So in this video, I want to take you through a very quick tour of problem 14 from the exercises in section 11.3. This is one of those that uses the concept of kinematics, which is the analysis of motion, analysis of displacement, velocity, and acceleration. And so it's a very basic problem. This is one of the problems, particularly because of the way the numbers work, this problem you would see on a calculator section of the test. So this is another good reason why I decided to build a video for this very quickly. We're going to do a lot more with these kinematic problems, but this will be a good starting point for us. So we were given a function, s of t equals t cubed minus 4t squared plus t, and we were asked to analyze that. The first question asked us to identify the velocity function, which is nothing more than the first derivative of s of t, which turns out to be 3t squared minus 8t plus 1. And just they asked for the acceleration, which is the second derivative of s of t, the first derivative of v of t, and that acceleration function, a of t, becomes nothing more than 6t minus 8. So some pretty basic stuff, really, in all honesty, at the moment. The problem then got into it, wanted to start finding some stationary points, and particularly some maxes and mins. And to do that, well, what would have to happen? We need to set our velocity function to 0, build a nice little sign chart, and take a look, where is the velocity changing? Now, this function did not factor nicely. We can get something out of the quadratic formula that you'll see, but if we have our calculator, one of the nice things we could do is just simply look at the velocity function on the graph. We want to set it equal to 0. I see that this velocity function, 3t squared minus 8t plus 1, has two roots. What's also very interesting, what do I notice? Excuse me, by staring at the velocity function graph, I can already identify what's going on at a couple of these stationary points. Before I hit this first root, which I think is at 0.06 or something along those lines, we'll go to the back page in a second and see that again. What do I know? The derivative, that function, is positive up here. My function has been increasing because I have a positive derivative. What happens right when I get on the other side of this root, where the derivative is equal to 0? The derivative is now negative. Positive derivative, increasing. Negative derivative, decreasing. And did we go through a value where the derivative was equal to 0? What we're doing here is really we're visualizing the sign charts that we build. We had a tougher function. We couldn't factor it, kind of couldn't go through some of the exercises, but by seeing the visual looks of how the derivative, the first derivative looks, in this case the velocity function, we can already say positive derivative up here, negative derivative down there. This represents a what? A maximum. Over here, what do we notice? This is our second root. It's right around a value of t of 2.5, as a matter of fact, on the scale here, right around just 2.5. What do we notice? Derivative was negative. Derivative equals 0 at the stationary point. Derivative becomes positive. What's that telling us here? We found a minimum. And so if we go back and just kind of look at the problem in a slightly different way, pretend that we didn't have a calculator and we had to do all this work, well, what would we do? 3t squared minus 8t plus 1 equals 0. Good old quadratic formula would walk us into some roots that are 8 plus or minus the square root of 52 over 6. Square root of 52, nothing more than square root of 4, square root of 13, 2 times the square root of 13. So we'd find out our two roots could live at 8 minus 2 root 13 over 6, 8 plus 2 root 13 over 6. And there's those two nice values, 2.54 and 0.131. Sorry for my misidentification a little bit. That's where the 2 points live in terms of their t coordinates. What would we do next? Again, calculator based. Take these two values that we've seen, 0.131 for t, 2.54 for t. Plug them into the original function, t cubed minus 4t squared plus t. Do this again. Hey, you got some ugly decimals to work with. This is certainly a calculator exercise. Get those points. We turn out that they are the y-coordinate, or the displacement value, is 0.065, negative 6.88. That's the worst displacement that I happen to have, and you can see it right here. I have a maximum displacement at t equals 0.131 with a displacement value of 0.065. My min, which is what part D is when t equals 2.54, my displacement is negative 6.88. And so the last piece, well, what does our graph tell us? We already talked this through, so let's just kind of take a look at what's the answer to question E. It says try to describe in words what's going on. Well, the object, and they wanted, I think, particularly from t equals -1 to +3 is where they were asking for this question to be answered. Well, looking again, what did we see? We saw that when t is starting at -1 all the way until it reaches a value of 0.131, we had a positive velocity. The displacement was moving forward. When we get to t equals when t equals 0.31, we're going to have a change of direction. The function starts moving what? In a negative direction. And it keeps doing that until when? Until it hits its next root at what? 2.54 as a value of t. As soon as it hits that, it now changes the direction and becomes increasing again. So there's kind of the bottom line. And again, we can use our derivative to kind of show us this. Increasing in the first batch, hit 0.131, starts to have a negative derivative. The function's decreasing for a good period of time, decreasing all the way until it hits again t equals 2.54, at which time, what did we notice? The derivative becomes positive again and stays positive the rest of the way. The function will continue. We'll have positive displacement. We'll keep moving further and further away as we go. So this is a good kinematic example. Hope it helps you out. Also understands, hey, sometimes we are going to have to get to the calculator. We're not going to have these nice and pretty factorable things all the time. And hope this helps you.